Well, hi, my name is Reema Nannapaneni, and today I will be talking about the Astrobiology Spectral Database. I have been working on this project under my PIs, Dr. Laura Rodriguez and Dr. Graham Lau. The goal of this project is to organize spectral data relevant to astrobiology, along with the experimental and instrumental metadata necessary to interpret those spectra. As a part of this work, I've also been reading through astrobiology related papers to understand what type of samples and chemical systems can actually provide this data. So, the first important question we need to ask is how do we identify and interpret organic molecules relevant to the origins of life? This is a very big question because just because we detect organics doesn't necessarily mean that life produced it. Abiotic chemistry can actually produce very complex distributions of organic molecules that can make it difficult to detect what the origin of these molecules actually is. In order to understand what molecules are present, we also need to understand the environmental conditions that produce them and the analytical conditions under which they were measured. This is where a database like the ASD becomes useful, because rather than treating the spectrum as an isolated piece of data, we can associate it with the chemical, environmental, and instrumental data to contextualize that measurement. So, what molecules are we looking for specifically? Key molecules in astrobiology can range from the smallest molecules, such as ammonia or methane, all the way to complex compounds such as fatty acids and nucleic acids. My research this summer specifically focused on amino acid synthesis pathways in terrestrial and extraterrestrial environments. Amino acids are the fundamental building blocks of proteins, which essentially makes them the fundamental building blocks of life. While finding these compounds on moons or planets such as Europa or Enceladus doesn't necessarily mean that they were produced by life, it would show that the environment contains the necessary conditions and precursor molecules to potentially support life. So my main work has been involved in identifying and organizing the metadata associated with these spectral measurements. For sample level metadata, we're primarily concerned with what reactants were used, how they were prepared, and the experimental conditions they were under. In terms of spectral metadata, we are concerned with what's the compound that was actually discovered, was it validated against a standard spectrum, and then also the intensity or the abundance of that compound within the reaction. The spectral data that we are mainly looking for comes from analytical techniques such as mass spectrometry or nucleic magnetic resonance spectroscopy. For both of these conditions, it's important to understand what conditions the compounds were analyzed in. So before we get any further, I quickly want to explain what we mean by spectral data and why it's useful. Two of the major techniques that are represented in the database are mass spec and NMR, as I just mentioned. So mass spec measures molecules based on their mass to charge ratio. This is useful because it can detect very small amounts of compounds within very complex distributions. We can also break these molecules into fragments, and those fragmentation patterns can provide clues about what the molecular structure of that compound actually is. NMR approaches this problem from a different direction. It uses a strong magnetic field to measure how atomic nuclei respond. This can, because the atoms behave differently depending on their chemical environment, the resulting signals can tell us a lot about the compound structure and its chemical environment. So together, these techniques give us complementary information. And by collecting these spectra along with the information about how they were generated, the ASD can provide a reference for researchers to use to identify and characterize unknown compounds. So as a part of my research this summer, I read through many research papers and I also reached out to authors to collect their raw data and model what a sample data entry might look like in the ASD. First, I included information about the study itself, such as the author information and the abstract. Then I included details about the experimental conditions, such as reactants, concentrations, solvents, and temperature. From there, I included details about the analytical method used, as well as the analysis condition. And finally, I included details about the compounds characterized and whether they were validated against a standard spectra. From here, researchers can also directly upload the spectra generated in their study for others to view. So As I mentioned earlier, my primary focus this summer was understanding where do prebiotic organics, specifically amino acids, come from. So the papers I focused on approach this from three different directions. The first asks how geochemical conditions control abiotic synthesis of organic molecules. The second places that chemistry into a realistic mineral environment by using chemical gardens as hydrothermal vent analogs. Finally, I looked at actual extraterrestrial material to determine what distributions of organic compounds are actually present. So in the first paper by Barge and colleagues, they looked at two simple organic precursors, pyruvate and glyoxylate. They tested these precursors in the presence of ammonia and iron hydroxide minerals, which can then create products such as alanine and glycine, which are two of the simplest amino acids. The researchers varied the iron oxidation state, the pH, and the ammonia concentration. This was necessary to mimic the very diverse environments of realistic planetary environments. What I found was really interesting because there wasn't simply one reaction outcome. As they increased the ammonium concentration, they did find that there was an increased formation of amino acid, but the distribution itself varied greatly dependent on the iron redox state as well as the pH. For example, under alkaline conditions with highly reduced iron minerals, glyoxylate actually dominated over glycine. Therefore, this tells us that the environment that these precursor molecules are in greatly determines the reactions that actually take place. This is important because we need to fully characterize the geochemical conditions of these environments to better identify the systems and conditions that might contain life. In the next paper, Marlin and colleagues studied chemical gardens, which are self-organized mineral precipitates, and they act as essentially laboratory analogs for hydrothermal vent chimneys. Hydrothermal vent chimneys have long been proposed as potential environments for the origin of life because they combine reactive minerals with pH and redox disequilibria. Sorry. And this is important because it's not just relevant to Earth. Even on ocean worlds such as Enceladus, hydrothermal vents have been proposed to exist. In this study, researchers reacted chemical gardens with the same kinds of simple organic precursors discussed in the previous study, pyruvate and glyoxylate. They also again varied the pH and ammonia concentrations to mimic the diverse environments possible. The researchers did note that the pyruvate reaction actually didn't yield the expected products such as lactate or alanine. They noted that the NMR spectra contained a very complex distribution, so it made it difficult to actually identify specific compounds. Under certain early Earth-like conditions, they did observe the formation of glycine from glyoxylate in the presence of ammonia. However, when they added salts intended to simulate the Enceladus-like ocean, they noted that glycine formation was actually inhibited. This supports the earlier idea that the surrounding geochemical environment strongly controls what chemistry organic molecules can actually undergo. Finally, my last paper moved away from laboratory simulations and asked what was actually found on extraterrestrial material. In this paper, Aponte and colleagues measured two CM2 carbonaceous meteorites, Aguasarcas, which is this meteorite over here, and Murchison. Carbonaceous meteorites are very valuable because their soluble organics preserve chemistry from the early solar system and subsequent processing within the parent bodies of the meteorites themselves. Rather than focusing on specifically amino acids, this study measured the different concentrations of amines, aldehydes, carboxylic acids, and cyanide. This is important because these molecules have all been considered to be precursors for amino acid synthesis in of meteoritic origin. So, in terms of the results, the researchers found that both meteorites dominated in carboxylic acid content, almost 2 magnitudes greater than any of the other organics that they found. Murchison overall had higher organic abundances, but Aguasarcas comparatively had higher levels of amino acids and acid releasable cyanide. But despite these differences in absolute concentration, relatively, they demonstrated the same molecular distributions. The authors argued that these similarities are consistent with the fact that the meteorites most likely experienced similar formation and alteration processes, which once again points to the idea that environment strongly drives product formation. Putting these papers together really helped me understand the purpose of the database in a broader way. The Barge paper showed that environmental parameters such as pH, redox state, and the minerals present can strongly determine which organic molecules form as well as their relative abundances. The Marlin paper showed that chemistry might operate differently within realistic mineral structures and the relevance of that for hydrothermal vent systems on early Earth as well as ocean worlds like Enceladus. And the Aponte paper demonstrates that complex distributions of related organic compounds in actual extraterrestrial material. From these three papers, the techniques used, such as NMR spectroscopy and mass spec, can help us identify and characterize these products. However, interpreting that data requires us to know the analytical and the chemical context. This is where the value of ASD is shown. It isn't just simply in having a large collection of spectra, it's to be able to make those spectra interpretable. If we detect an amino acid or a carboxylic acid in a sample, we want to know what chemical pathways could actually produce it. We want to know what the environment is that could produce those pathways and whether similar spectra have been observed under other laboratory or realistic environments. This is especially important for biosignature detection because abiotic chemistry can generate structured organic distributions, but it might not necessarily be produced by life. By linking the spectral measurements with the detailed metadata and experimental context, the ASD can help us move from simply identifying a molecule to actually understanding what that molecule tells us about the environment and chemical history. Most importantly, the ASD helps the astrobiology community by providing an open source reference library. One of the biggest issues in exploring origin of life issues is that the raw data is often not available for other scientists to use, which is where ASD seeks to solve this problem. By providing a shared platform available to everyone, researchers from all across the world can access the same data. From here, by preserving detailed experimental and instrumental metadata, new discoveries can be standardized within the ASD. This would make it easier for researchers to cross-compare and validate data, and in doing so, the relevant organics as well as the reactions and environments can help uh, better characterize the organics produced. At the same time, gaps in the database can be used to identify new questions about compounds, environmental conditions, and the environments that produce them. In that sense, the ASD is a vital tool, both as a reference library for prebiotic chemistry as well as a tool for future experimental design and validation. Thank you.
Fantastic job, Reema. It's been such a pleasure having you in the program with us. Are there any questions that people want to drop in the chat or raise a hand for to ask Reema? Sanjay?
Reema, this is a very nice presentation. Thank you.
Thank
So,
you.
after reading those papers and your newfound appreciation of the importance of geochemical environment in driving chemistry for compounds relevant to the origin of life, do you personally think that the origin of life could have happened at a single geochemical location, or that you needed several geochemical locations to form the products that then somehow found each other for the origin of life to occur? What's your opinion?
I've actually always really uh what's the word? Subscribe to the belief that life originated in these hydrothermal vent systems. But even within the systems found on Earth, you have very different environments found. Like you have hydrothermal vents that are very acidic environments, or hydrothermal vents that are very alkaline environments. So I think that in that sense, it's necessary. Life could start multiple times across. I do believe that life could start multiple times across Earth. Do I think that they might have needed to find each other? Possibly, but I feel like the probability of that happening, just given ocean cycling and everything, is so infinitesimally small that I feel like it's more likely that life originated on its own within its own environment, across multiple places, like on Earth or even like Enceladus or Europa, if there's life there. Then specifically that you have compound A or like precursor A in one area meeting up with precursor B from a different area that all combine to form an actual the actual like original an common ancestor, say. I think that is one of the hardest parts of origin of life questions, obviously, is that there's so many variables, and it's like even if you get partway there in one environment, you might be missing the link that can then connect it to a later part of the equation. So it's really hard to, make a good educated guess of, yeah, it all formed entirely within one area, or it needed to meet up with molecules or precursors from other parts of the world to then be able to develop into something that we know more similarly to life these days.